Hello everyone, this is Miss Hu, your physics teacher. In this video, we're going to go through melting, boiling, and evaporation, which is one of the topics in IGCSE physics. By the end of the lesson, we will be able to describe melting and boiling in terms of energy input without a change in temperature, describe condensation and solidification in terms of particles, explain the cooling process of evaporation, as well as compare and contrast boiling and evaporation. Now, first things first. Let's recall what we remember about internal energy. Internal energy refers to the energy that is possessed by particles in a body. That means body could mean object, okay, substance, material. And let's recall that there are two types of internal energy. There is kinetic energy, which refers to the energy due to the motion of the particles. Now, if you can remember what you have already learned before about the kinetic theory of particles, all particles, sorry, let me rephrase, let me start it again. All matter is made up of tiny discrete particles that are constantly in motion. So even if it's in solid form, they're moving, but just vibrating in place. Liquids and gases would be moving randomly, translating and rotating. The kinetic theory possessed by the particles is directly linked to the temperature of the object. The higher the kinetic energy, the higher the temperature of that object. Internal energy also includes the potential energy of the particles, which refers to the energy that keeps the particles in their positions. This is related to the state of matter. So when an object has lower potential energy, when it has lower potential energy, it has higher intermolecular forces, so that keeps them in solid state. Okay? The greater the potential energy, the further apart the particles would be because the energy is pushing them apart, so that weakens the intermolecular forces and that changes the state of the body. So as it changes state, it changes potential energy. What you have to recall over here is that internal energy refers to the total of both kinetic energy and potential energy of the particles in that matter. If heat is applied, the internal energy of the object increases. Where does this energy go to? It could go to the kinetic energy, or it could go to the potential energy. So if the internal energy increases, causing the kinetic energy to increase, temperature increases. If the potential energy increases, then it changes state. But remember that only one type of energy can change at a time. So let's say you've got kinetic energy and potential energy. Okay, so if heat energy is applied, if the kinetic energy increases, the potential energy remains the same. If the potential energy increases, the kinetic energy stays the same. You won't have situations where both increase at the same time, because otherwise, when the object is absorbing heat, it's like, where does the heat go to? Does it go to kinetic and potential? They're fighting for the energy. That kind of like seems to be a waste of effort because they're competing. So it's one at a time. So to illustrate this further, we can look at the heating and cooling curves. Now you've learned this before, so let's just quickly recall what we've learned. Let me move my face out of the way, it's not moving. Ching, 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 ching. All right, so these are the general heating and cooling curves for most objects. So on the left-hand side, we have the heating curve here, and you can, if you recall what you've learned, right, you've got a situation where if you apply heat, the temperature the temperature increases, and this is where the kinetic energy increases. Now, remember, kinetic energy increases, but the potential energy doesn't change, which means that if this was solid state, all the way solid as the temperature increases. Now, once it's hit the melting point, then the potential energy increases, but the kinetic energy stays the same. So that's why during this stage, temperature doesn't change, but it's actually changing state. It's melting from solid to liquid. Once it's completely liquefied, completely liquid at this point, then the kinetic energy would start to increase again. But it's still in liquid form, so the potential energy doesn't change. So that's why you find, okay, another increase. Then when it hits boiling point, similarly to melting, the temperature remains the same. So that means the potential energy now is going to increase while the kinetic energy stays the same. So that's why temperature remains the same until it's completely turned into gas. Then if you continue to apply heat, then temperature would increase. The cooling curve is the direct opposite. It's just that now in this case, instead of absorbing heat, it's losing heat energy. So same thing, kinetic energy is decreasing while potential energy remains the same. When it reaches condensation point, the potential energy remains the same. Sorry, potential energy decreases, kinetic energy remains the same, and so on and so forth. So that's why you see sometimes temperature increase, then stays the same. Temperature increase, stays the same. Because if you look at it, a lot of people always think, oh, if the temperature doesn't change, that means that there's no heat being transferred. You know, heat is not being absorbed. Oh, there's no heat loss. Now, that's not true. Because if we were to look at this experiment basically is showing, not showing, this experiment is done to investigate the temperature changes when you're heating an object. So let's say, for example, we took ice, we put inside here, we measure the temperature every 30 seconds, and then we plot that graph out like for just now. And then you think about it, okay, as you're heating and you measure the temperature, you'll find, hey, at one point the temperature remains the same. Now, is heat being supplied? Obviously, there's a Bunsen burner here, and is heat being absorbed? Where's the heat going to go, right? So yes, it is being absorbed, but where does the heat go to? There's no temperature change. It goes into the potential energy. So the heat energy is used to break the bonds between the particles in order to allow for the change of state. So even without a temperature change, there is still energy increase. In this case, in the form of potential energy. Now let's go into evaporation. So what is the process of evaporation? Okay, so for this particular slide, I have not prepared anything because I just want to draw it out so that you can see. So I'm going to revert to slide view here. I'm going to move my face this side. Yes, I know there's a bunch of slides. Just focus on what's going on here, okay? So let's say this particle represents some water particles. Let's just put a few more particles here. So many of you have learned this before, but I'll just explain again for the benefit of those who have not learned it or have forgotten. For evaporation to happen, the particles have to absorb heat from somewhere. So let's say this particular particle is absorbing heat from the other particles. So let's say, wait, I'm not doing this correctly. Okay, so I'm going to draw some arrows here. These arrows represent heat energy that is being absorbed. So the direction of the heat transfer. So this is the direction, what am I saying? This is the direction which the energy is moving. Now, let's say this particle, I'm just going to put a different color just to, to make it clear that it's a different one. Okay, this particular particle is going to make its great escape. So it's absorbing energy like, okay, guys, come, give me what you've got. So they're throwing the energy. Okay, you can make it. Go, go, go. So this particle would absorb heat energy from the other particles, and once it's absorbed enough energy, so enough heat energy, this is converted to kinetic energy, so it's going to vibrate and eventually, okay, the lines are moving with it. Yeah, okay, it's going to make its great escape. All right, so it's going to go out. Okay, so now this particle has absorbed heat energy from the other particles, which means that these particles have lost their energy. So what you'll find is that the lower energy particles would remain in the liquid. So I'm going to type up what's going to happen here for your benefit. So the more energetic particles will leave the surface of the liquid. Okay. The particles have absorbed heat energy from other water particles, or liquid particles rather. It's not water only, my bad. Liquid particles. The lower energy particles remain in the liquid. Okay. So this is why evaporation has a cooling effect because the lower energy particles remain in the liquid. So if you are asked to explain how the process of evaporation creates a cooling effect, I'm just going to change the color here so that hopefully it's easier to read. Let me add in the words here. Process of evaporation creating a cooling effect. And I'm going to make this white in color because I like. Oh, that's not white, that's gray. You know what? I'm just going to go with it. So if you were asked to explain how evaporation can create a cooling effect, there are two things that you must mention. You must mention the water particles and you must mention the energy. So remember, particles and energy, you must mention that because the particles absorb energy, they leave. Particles with lower energy remain in the liquid. That's why the remaining liquid is cooler. Okay, moving on. So how does sweating cool us down? So the sweating process, how it cools us down is because of evaporation. Exactly the same concept as just now. In this case, the sweat is on the surface of the skin. So sweat, which is liquid particles, right? It absorbs heat energy from the skin. So the skin would transfer heat energy to the water particles. The water particles will absorb and gain enough heat energy so that it becomes in the gaseous form and then evaporates. So the skin particles have lost heat energy and that's why the skin feels cooler. And that's how sweating cools us down. Now let's talk about the factors affecting evaporation. And I also didn't fill this up because I want to explain this to you as we go along. So what are the factors? Well, for one, humidity. Oops. Humidity. Humidity is the presence of water vapor in the air. So think about it. If there's more water vapor in the air, is it easier for the water particles to join? It's more difficult, right? So normally the drier the air, then the more water there is, the more evaporation happens in order to fill up the air with more water. So higher humidity, lower rate of evaporation. So I'm going to write the factors on the column on the left and then the relationship on the right. Now temperature also affects it because higher temperature, there's more heat energy. Therefore, there will be a higher rate of evaporation. So this is, of course, temperature of liquid. So higher temperature, higher rate of evaporation. Atmospheric pressure is also a factor. Atmospheric pressure refers to, imagine it is the liquid surface, refers to the pressure of the atmosphere air pressing on the surface. Then you think about it. If the atmospheric pressure was higher, is it easier or more difficult for the water particles to leave the surface and become gas? Obviously more difficult. So higher pressure, lower rate of evaporation. There's also movement of air. That means is there wind, like you blow, right? So if you, or there's air blowing, then the air helps to add energy to the water particles to leave the surface. So that's why when something is hot, you blow, make it cooler, right? So higher movement of air, higher rate of evaporation. Next, surface area. So logically, small surface area, large surface area, because it's on the surface, right? So higher surface area, higher rate of evaporation. So that's why when we want to dry our clothes on a clothesline, we don't fold it up. We try to make it, we try to spread it out over a wide area, like our towel, hang it out wide so that it's easier for it to dry. Lastly, boiling point. Higher boiling point, lower rate of evaporation, because if a liquid has a high boiling point, that means it needs more energy to be able to convert it into gas form. And that's also related to evaporation. I'm just going to switch the slideshow back on so that you can read this more clearly. Let me move my face out of the way. Okay, next, let's look at boiling versus evaporation, which is a very, when it comes to the change of state, there's always this comparison because both boiling and evaporation changes the state of liquid to become gas. Yet, in spite of that similarity, there's so many differences. So let's look at the differences. So again, this is blank because I want to discuss this with you as we go along. So when it comes to boiling and evaporation, the only thing that is similar about both processes is that the process changes the state from liquid to become gas. But otherwise, there are so many differences, and these are the differences. Temperature occurrence means at what temperature does boiling and evaporation occur? Think, think. So boiling only happens at boiling point. Evaporation doesn't need any particular temperature, right? So it happens at any temperature below boiling point. Just going to stretch this out a bit more. So, yep. Temperature change refers to, does the temperature change during the process of boiling or evaporation? Now, we've just covered all this in the beginning, right? So when boiling occurs, it's a change of state, heating curve, state line, right? No temperature change. Evaporation, what did we just go through? Cools us down, right? So the temperature decreases. The rate here refers to how quickly these processes occur. So which one's faster thing? Boiling or evaporation? So obviously boiling is faster. You boil water, okay, it takes some time, but very fast become gas. Whereas evaporation takes a long time. So that's why when you want to dry your clothes, you got to hang out and leave it in the sun for a few hours. So it's slower. The region here refers to where in the liquid does boiling and evaporation occur. So boiling happens throughout the entire liquid, while evaporation happens only at the surface. Are there bubbles when boiling occurs? Yes, there are bubbles. Evaporation? No bubbles. Do they need a heat source? Boiling? Yes. That's why when you want to boil water, you have to plug in electrical heater kettle or put it over the stir fire. But evaporation? No need, because the energetic particles just steal the energy from neighboring particles. Right, let's put the slideshow back on. And there you go. These are the main differences between boiling and evaporation. Let me move my face out of the way. It's not moving. Here we go. There we go. So I hope you found this video educational and helpful. Don't forget to, okay, my face is being blocked by the logo now, right? Yeah, don't forget to like and subscribe for more lesson solutions and exam strategies. Now, if you have any requests for any particular video lesson that you'd like me to cover, feel free to drop them in the comments and I'll do my best to get back to you on that, right? Okay, thank you for watching and happy studying.